Let's take a look at another integral and ask whether the integral converges or diverges. How about the integral from 2 to infinity of 1 over root x minus 1 dx? Here's a graph of it. It looks pretty much like all the other graphs we've ever seen in this chapter for horizontal integration. So remember, we can't tell by eye whether this curve approaches 0 fast enough for the integral to converge or diverge. There are some cases where this function approaches 0 fast enough for the area to be finite. There are others where this function still goes to 0. I don't mean this function, but just generally in this graph. Still goes to 0, but the area underneath is infinite. So what can we do with this? Can we use a horizontal p-test with p equals 0.5 maybe? Well, what does the integral, p-test usually starts at 1, but if you start at 2, you just cut off a finite chunk of area. It's not going to affect whether the overall integral is infinity or not, because we're dealing with stuff away from the vertical asymptote. So x to the 0.5 is like root x. Does that integral converge or diverge? That integral diverges. That we saw that near the beginning of the chapter, but here we can say it's because p equals 0.5, which is less than 1, and the horizontal p-test says if p is less than or equal to 1, then that horizontal integral diverges. How does this function relate to that function? So let's think about 1 over root x minus 1 and 1 over root x, or 1 over x to the 0.5. Which one of those is larger? Well, here the denominator is smaller than the denominator here. I'm still avoiding divide by 0 because root 2 is 1.4-ish, and subtracting 1 still keeps us above 0. So here the denominator is smaller than this, so the fraction is larger. So the denominator is smaller, so this denominator is smaller than root x, so the fraction is larger. So if we went and graphed the this curve, which we kind of already did, and then graph this curve, what would we see? We know that the original curve is larger than 1 over root x. So 1 over root x is something like this. And this curve is f of x. So what conclusion can we draw here? Think about what this observation in that graph tells us. We can say, since the integral of 1 over x to the 0.5 dx is smaller than the integral we're doing, on the range 2 to infinity, and this integral is infinity, it's an infinitely large area, it must be true that this integral has to be somehow bigger than infinity, right? So the only way to do that is to be infinity. So the integral diverges. So that's another direct comparison. We were comparing the integrand of one thing to the integrand of the other thing. One was always below the other, so the integral was always below the other integral. And knowing that the easier integral was infinity, we could conclude that the more complicated integral was bigger than that, must also be infinity. So can we summarize by saying it's helpful to know what? It's helpful if you know that your integral is less than a convergent integral, because you can make a conclusion there. What would you conclude in that case? Then your integral converges. Or it's also helpful if you know what? If your integral is bigger than or equal to a divergent integral, an infinite one. We're assuming all these integrals are positive. If they're negative, you just have to think about standing on your head, thinking upside down. But this is the main intuition. If your integral is bigger than an integral that you know is divergent, then your integral is divergent. So the question is, what is not helpful to know? So can you take this logic and say, what's missing here that I didn't label as helpful? What if your integral is less than or equal to a divergent integral? Does that help? Well, even if it's a strictly less than, this divergent integral might be a kind of bigger infinity than your integral might be, so your integral could still be infinite. What else isn't helpful? Think about another option here. If your integral is larger or equal to a convergent integral, that is one that's finite, knowing that your integral is bigger than some finite number doesn't tell you that your integral is finite. Your integral could be infinite. So this whole direct comparison thing, it's kind of like a one-way valve, or just two different one-way valves that kind of work in these situations but fail to work in these situations. Here's a kind of example, not necessarily from my own life. Let's say a kid says they brushed their teeth, and you go in the bathroom and check that their toothbrush, is it dry or is it wet? If it's dry, you know they didn't brush their teeth, within the last half hour or whatever. But if the toothbrush is wet, does that guarantee you that they brushed their teeth? No, maybe they were sneaky and just ran the toothbrush under the water and didn't brush their teeth. So it's a case of necessary condition versus sufficient condition, or kind of enough evidence one way is good, but not, the other way doesn't give you enough evidence. So it's really tempting to say we can make conclusions in all of these cases, but in these cases, no conclusion is possible from these observations. You have to find a different integral that gives you observations like this. So that's the direct comparison tests.